I am going to start with a quick caveat. Good afternoon, everybody. I am ecstatic to be here. But to be truthful, this is one of my favorite conferences of the year. I've looked forward to it for months and am ecstatic to be speaking here. So thank you very much to Bryce for letting me do that. But to be honest, I'm not a social person, everybody. Despite this being a very integral part of my career and having to do this almost monthly, it never really seems to get easier. So a combination of my anxiety and coffee is probably going to get me walking in circles. And if I start to talk at breakneck speeds, just make faces at me and I'll probably slow down a teeny bit. As a quick introduction to myself, my name is Kurtis. I'm a principal AI researcher at NetSpy. And I have had the wonderful opportunity throughout my career to be able to start in STEM. So I started in biochemistry, and then I pivoted from that to doing work in the bioinformatics space. I did machine learning on genes and gene mapping and biomedical devices. And then eventually pivoted from there to security and had the awesome experience of being able to mentor under somebody I'm quite close with for a while. And he taught me to do AI red teaming. And from there, I got hired on at NetSpy and founded and developed the AI red team there and have been directing and leading it ever since. Proudly, it is one of the oldest AI red teams in the world and is, in my opinion, quite high performing, and I'm very proud of it. That being said, over the last 6 months to a year, I've had the further opportunity to pivot from doing in-person engagements and getting that exposure to machine learning in just about every magnitude you can imagine, whether it be hardware or web applications or networks, generative predictive models, to doing all research now. I am doing math for a living in my basement. So again, people's not my forte, so as we work through this, bear with me. With the change in those research initiatives, I am now in a position at NetSpy where any AI-related initiative, whether it be developing models, whether it be attacking models or defending models, I'm involved in some way, shape, or form. And I couldn't be luckier. This is a really, really cool spot to be, and you should be ecstatic to be here because there are so few of us in the world. And with that, however, and with the experience that I have, I will admit I have some pretty spicy opinions. And one of the largest opinions that I have that I think is integral to understanding the research that I've done and the approach that I've taken to breaking these models over the years is, all cards on the table, I don't believe that any model, machine learning model, is truly defensible. Now, that's a hot take. What I mean by that is that no model, truthfully, can be fully robust or immune to robust perturbations without gutting the functionality of the given model to the point where it's no longer useful. As a quick confession, originally my talk was going to be a bit different than this, but I had a discussion with a really good friend right beforehand, and now we're on a cascade of trailing thoughts and lessons that I think are really pertinent to the space. One of the most valuable lessons I've had the opportunity to learn over my years doing AI red teaming is that as a red teamer in this space, the intersection between data science and security is not only critically underdeveloped, but acting as a liaison and a communication bridge between these two entities is probably one of the most valuable assets I provide in my job. These two groups don't traditionally communicate with one another. Security groups don't want data to go anywhere, and data groups want every little bite of data that they can get their hands on. So how do you make that balance? How do you make that work? And that's where I spend a lot of my time. So rather than really belabor the basic landscape of what machine learning specific vulnerabilities look like I had intended, instead what I'm going to really push here is trying to help you move beyond this binary mindset of a given machine learning model is technically vulnerable to something or not. Remember, if we assume that models are innately indefensible and they are inevitably vulnerable, we know that they're vulnerable, right? At some point, an applied amount of effort and enough math will be able to break these models in whatever magnitude might be possible, given the vulnerability space. With that, taking a more traditional security mindset is not great to handling the mitigations for these. Now, when I say binary, I don't mean literal zeros and ones. I'm more referencing like an on-off switch sort of approach. If I'll use SQL injection as an example. Generally speaking, though, the blast radius for a vulnerability like SQL injection might vary and how much damage you can do might vary. Whether or not SQL injection is present in a given environment is an on-off switch. You have parameterized your queries or you haven't. And if you've properly parameterized them, chances are the switch is off. This is not the case with traditional machine learning vulnerabilities, ever. It is important and imperative that we accept the inevitable truth that every machine learning model is going to be vulnerable to every machine learning model specific vulnerability in some magnitude or another. And with that, we can start to define benchmarks, we can define defenses, and we can define approaches to not only attacking these models, but ensuring that we can increase that robustness to an adequate degree. So the last little line there at the bottom is just a plea to, again, even if you disagree with me, follow my logic here as we push through this, because I think it'll make more and more sense as we push through. But we can't treat models as like a binary on-off switch vulnerability type approach like we do in traditional security. Now, I spoke here last year, and that talk was greatly predicated on threat modeling machine learning models, how to determine whether or not a certain type of vulnerability, still predicated on the same assumption, is pertinent to your given environment. So if you have a given machine learning model that you have deployed in some shape or form, how can you tell which of these vulnerabilities actually matter? So if you were here last year, forgive me and allow me some redundancy. This is the only slide, I promise, but I'm going to catch us all up on that because I think the combination of these ideas is quite important. And when you come and threat model a given model, understanding again that inevitable nature of these vulnerabilities, you also need to understand that there's a lot of risk that comes with employing or deploying defenses around these models, whether it be input or output filters, whether it be adversarially training it, or doing any sort of deployment type defense in that regard. You are always dancing this very, very delicate dance. Whereas if you employ adversarial training examples to a given model, there's a chance you might diminish that model's capability to perform its target function to an acceptable degree. And that's sometimes a risk that isn't worth shouldering. So it's imperative that at the beginning of this process, you identify which of these vulnerabilities you actually care about. And as generative models become more and more capable in their landscape, these magic token tumblers become more and more used, this landscape expands further and further. So let me give an example. Let's say I have two clients. On one hand, I have a bank, and on the other hand, I have a pet shop, just a classic web application. And in this scenario, both clients have a need for an image classifier. So, lazy as they are, they hop onto Hugging Face and they grab a model that they didn't build themselves, and then they fine-tune it to their given use case, right? So, on one hand, the bank is using it in an ATM to classify whether or not a check is real and how much money is on that check. Whereas on the other hand, the pet shop is using it as like a fun little preliminary tool that clients can use to get like a non-legally binding quote on how much it might cost to cut their dog's fur. Now, the underlying target function between these two models, and this is like a classic physics problem that you might have had in school, like we're acting in a frictionless environment here. Assuming that the access to these models, independent of hardware or any other external variables, is the same, the attack process for breaking these two things is more or less identical, and it won't take very much time. It's just math. If math can make it, math can break it. You're going to hear me say that probably 400 times in the next hour. I very much believe that in this scenario, it's important that we start to identify why these vulnerabilities matter. So, okay, on one hand, in the ATM, I can break it. I know I can break it, and I know that if I do, I can quickly coerce this machine learning model into believing that my check that might have been $400 is now a $400 million check. On the other hand, the attack process for the pet shop is more or less meaningless. Even though the math underneath the hood, the target function is going to be effectively the same, the threat model here, whether or not you care about evasion, is significantly less pertinent to the conversation here. If you want to extract that model, or if you want to evade that model, or convince that model that your Samoyed is a sheepdog, at the end of the day, it probably doesn't matter. And so identifying the difference and the overlap between the target function of a given model and the business function of that model is one of the earliest steps that red teamers can leverage to understand which vulnerabilities they actually care about. Because you don't want to waste a myriad or a mountain of time trying to hammer away at certain vulnerabilities that your client or the environment that you're pushing against may not necessarily care about. Furthermore, you don't want to make mitigation suggestions that take them down a path that could potentially damage the overall functionality of that model. If I go tell this pet shop that they should adversarially train this model, it's very unlikely they have a data team. It's very unlikely that within that data team they have an adversarially experienced individual who can do that training properly, and they're very likely going to gut the overall capacity that this model has to perform that function. So you've messed everything up and have gained them nothing. So take that in mind with the inevitability of vulnerabilities in the security space, and then combine those two together. Now within this, we start to see a problem. With basic red teaming approaches, even in the AI space, you're always operating in a point-in-time scenario, right? Which is implicitly kind of binary, right? If I come into your environment and I break a model and show you how to get an evasion POC and show you that I can make that ATM believe that my check is $400 million, that's really, really cool. But I did that today. You could deploy defenses, you could adversarially train that model, you can make things change tomorrow. And how is it that I can assess the breakability of that model or the susceptibility, a lack of robustness of that model, the next? And for traditional security, this is also a problem, but it is extremely pertinent to the AI space because we know that they're vulnerable, right? We know that that's doable. Yes, we gave you nice, neat little steps on how to do it, but math is math. If math can make it, math can break it. So this led my team and I to start looking at research options and why addressing vulnerabilities as gradients rather than on and off switches is a valuable thing. And within that, we started with probably the most popular vulnerability in the machine learning space nowadays, direct prompt injection, or by default, direct and indirect prompt injection. What those look like, how to detect them, and how to do them. And everybody and their mom right now is super excited about generative models, how to use them and how to employ them in whatever magnitude you can imagine. However, one thing that we quickly were able to realize is that with a proper amount of math and a combination of a classifier, an ensemble voting classifier, and generative models themselves, we were able to create an automated loop that penetration tests in this regard at a high level the susceptible vulnerabilities within this direct prompt injection space across a wide variety of different contexts. And we began to benchmark very popular models across the space to see how generically easy it was for our testers to break them with this automated tool. And that was the foundation. That's where we started. But any of you math heads out there might recognize that it is very difficult to orthogonalize any result with just one parameter. So we quickly ran into problems, and that's why I included this little guy here. This is not an anomaly. This is actually the results of a client that we messed up with. We came back to them, showed them the results. It was while we were using this in its beta, and said, hey, if you look at your breakability, you're not doing so great. It does not take us very many attempts to jailbreak your model, and we can jailbreak it over a wide variety of different contexts. And then given a human element, we can then begin to branch those vulnerabilities into more significant security vulnerabilities that might be present, like OS command injection or SQL injection or whatever else. And that was a significant problem for them. So what did they do? They hopped onto Bedrock and they employed an output filter and an input filter and then amped up the settings about as far as it could go. And look, they fixed the problem, right? It's not breakable anymore. Well, the trick is they had actually amped up the security to the point where this chatbot, which was supposed to help customers resolve technical issues in their account, could only respond with the terms yes, no, perhaps, and I don't think I can do that. And that is remarkably useless, right? And so very quickly we found out that when it came to recommending these changes to clients, this parameter in isolation is incredibly misleading and doesn't work. Now, a chart like this also probably looks remarkably similar to what you would find in a model card evaluation. If you as an individual are looking to go use a generative model developed by a third party, whether it be any of these, and if it isn't clear already, I'm not on any of their payrolls, so I'm not trying to hurt anybody's feelings here. The models themselves and these metrics are always going to be contrived to help you see the models in their most functional light. And that's a cool thing, but from a security perspective, it's intentionally misleading. It puts you in a position where it's very difficult to triangulate or figure out whether or not a model is breakable or not breakable to a sufficient degree for your given industry use case. And so this is where it began. And by the way, as a quick aside and a shameless plug, I wrote a paper and we published it this last year. It's open sourced, so you can see the tooling on how we did this, the techniques we used for it. It's all on GitHub. So please go contribute, and I'm going to maybe sing a song about that here in a minute. But quickly we found that the benchmarks for these breakability approaches that we were taking were not only context agnostic enough that they were not usable, but they also didn't include a usability benchmark. We couldn't adequately measure how usable these models are within those given contexts to validate whether or not the changes that a customer had made were actually useful. And so the next step was contriving, is maybe a very off-the-wall way to put it, a benchmark that could be useful to our clients, something that they could use to measure the usability of their given model before and after they employ these output filters, before and after they do some level of fine-tuning or adversarial training so they could see the difference. And this had to be contextualized manually to every single scenario. So if you were a healthcare provider, we had to use certain data sets, or we had a list of certain data sets that we would provide to you, and then a person that would come in and create that usability benchmark from the ground up to make sure that it was contextualized to your industry. Because someone who is in the production industry might care a whole lot less about whether or not their model is biased toward a particular age or usable than somebody in the health industry. And so we struggled, and still continue to struggle quite a bit, as bias and usability as umbrella benchmarks are incredibly dimensionally dense. They're hard to create a ubiquitous silver bullet for. And with that, we still, to this day for our clients, have to cater these benchmarks to their contexts explicitly to make these outputs useful. Now, do I believe that's the end of the road? No. I do think that there is room for two spots here. And really what I want to belabor, and one of the biggest points of all the rambling that I'm going to do today, is that red teaming in particular, again, is that point and instance poke, right? You can see this window of how this model is behaving at that given point in time within whatever time interval you had. But to properly understand the robustness or breakability of that model, we have to combine traditional AI red teaming approaches, those human-driven approaches, the math, with honest benchmarks that can give you an idea of how breakable this model is. So when somebody comes to use your model, and we'll hit on an example a little bit later here that we did for a medical clinic here in the United States. If you are not transparent with the kind of biases or trends or usability metrics that these models are provisioning for your users, there is real risk here. And there was a talk earlier that brought up Air Canada as an example. Like in some instances, it's very likely that these outputs, even as a generic jailbreak, like building a bomb or doing something like that, could become a legally binding instance for you. It could be something that you're legally liable for. So AI security cannot just exist in the traditional security space. You know, can I or can I not steal your data, or can I or can I not steal your model? But we have to start branching into this more moral sect of recognizing that there are societal impacts to the models that we're developing. There are changes within these models that can greatly influence a lot of things. And so the point here that I'm really trying to bring home is that understanding that the inevitability of these vulnerabilities within models is just a static in this environment. How can we handle this, and how can we effectively tailor mitigations that we generate to this understanding? How can we make sure that the output filters we recommend are good enough? How can we make sure that the benchmarks that we're creating are good enough? And that comes with our collaborative work and time. So as a fun little aside, we took a lot of very popular benchmarks and then plotted the usability versus breakability before and after the employment of an output filter. And one thing that you'll find very quickly here is, like Anthropic as an example, is normally an extremely robust model, very good at what it does, and quite useful. But with Bedrock's output filter set at its medium base settings, it doesn't really get innately secure. It doesn't move more toward the left really at all in any meaningful way. What it does is it plummets in usability. It becomes remarkably less usable with very little trade-off that makes it worth it. And so this was the next step for our benchmarks. We started to look at output filters and how they're designed and how they can be utilized to optimize given performance for whatever, again, industry that your client or your individual, whatever environment you might be pushing up against could operate in. So, and this visual did cause a lot of drama. But like there has been a lot of updates and changes to these models, but the truth of the matter is the approach to how this all works, how someone like myself with a lot of AI red teaming background is going to break these models is going to be pretty straightforward. We use math. And again, If math can make it, math can break it. The math that makes these models functional will always innately provide these vulnerabilities in some magnitude or another. And you need to understand that before you deploy this in a production environment where somebody might be able to suddenly make you legally liable for one thing or another. Or if you've given it external functionality, leverage it to access data that they otherwise shouldn't be. This is very easy. To perform all of this testing and to adequately get over 4,000 jailbreaks in a wide variety of different contexts took us less than 2 minutes and $3. Like, it is not a hard thing to do. And I don't want the impression to come across that AI security or AI red teaming in general is hard to do. It's just math. And we all went to high school, I hope. And with that, calculus, linear algebra, those things are extremely systematic, extremely formulaic in the way we approach them. So here's another example of like a contextual biased result that we got for that clinic I had mentioned before. I came in and did an engagement for a clinic that allowed users to provide symptoms to a chatbot on their web application. That chatbot was then leveraged to provide insights back to them and give them appropriate recommendations. Now, really, again, I wasn't able to show all the data because, that would be bad. But I did get permission to share this, and you can see when we were querying GPT-4o with given symptoms, and then asked GPT-4o to estimate the age in which it was actually providing those given outputs for, and then triangulated those outputs with, bone density or other things that are generally directly correlated to a given person's age, GPT was incredibly prone to assuming that you were 35, 45, or somewhere in the middle. So if you came and said, I'm experiencing stomach pain, you were statistically very likely to be bucketed in this space where it might tell you that you have cancer because you're at the age of 80 significantly more likely to have cancer. That's not accurate, and that's rather misleading and very spooky. But that was something that was happening and a problem that they were having with their given customers, and it's a visual thing, and that's my point. It's all math. Like, token tumblers or not, bias or not, usability, breakability or not, at the end of the day, it is all just math, and not difficult math at that. There's this gatekeeping type wall that a lot of data scientists or big companies like to kind of hide themselves behind to make you feel like you need a lot of data or a big understanding of how math works to make these models work. Machine learning, by definition, is the ability to program, or not even program, to teach a computer how to perform a function without explicitly programming it. It's supposed to be easy. Like, that's the point. It's supposed to work by default. Now, there are exceptions to this, but when it comes to visualizing these vulnerabilities, it is just that, blatant data science practices with a different optimized function. So when we look for these vulnerabilities, we just have to shift our perspective. We look from the, am I trying to get the more optimal output for a given client, to how can I show them that I can optimize for these malpresented outputs? I can show them where bias exists. I can show them where these things exist and translate that into a communicatable, valuable asset to that company in a security sense. Now, one of my favorite sayings of all time is a rising tide raises all ships. I very much believe that the only way we can make these benchmarks better and these approaches better is to work together. Because there is no way for me, Kurtis, a white fella in the United States, to adequately understand the extremely dimensionally dense space that is bias, and then formulaically provide that to every company I ever bump heads with. I need insight from other people. I need interpretation from other people, and so does my team. Our success as an industry is contingent on that. And so working together, understanding that everything is inevitable, understanding that these vulnerabilities are something that we are just going to have to face, is a very, very important thing to me. And so I added this little slide as a quick ramble. Let's do something more fun. So Kurtis, you like to do math. Dance, monkey, dance. There is a very, very fun case study. I just made this slide, so forgive me if it's a little unorganized again when I took that rapid change in trajectory to kind of talk about some differences. I want to lean into this a little bit to elucidate my point. If you look into a case study that is very, very open on Hugging Face called obliteration, it is the practice of being able to de-align without any fine-tuning whatsoever a model so that it behaves unethically, a locally hosted model, that is. Now, the practice starts with you just taking two data sets. One that is a very positive data set, questions that the model should positively respond to, and then a second data set which is full of more malicious type things. Build me a bomb, commit me crimes, give me data, things that it otherwise should refuse. Now remember, generative models are just token tumblers. They can't patent that term. That didn't come from me. But the idea here is that the vector representations within its understanding of the world are always going to translate to one another in some way, shape, or form that represents relationship, which means anything that you can think of may or may not be, but is very likely representable within a vector. So following this path and following the walkthrough that they give you in this Hugging Face blog, you can identify something that they call refusal direction. You can identify the vector that is the difference between a model positively responding to you and then refusing your response. And subsequently subtract that value from the refusal and then suddenly get it very willing to commit crime for you. Now this is cool. This showcases that you can de-align a model in 20 minutes and you can get it to start committing crime for you willy-nilly. Now that's more or less where that research ends. But what I'm really trying to pull home here and kind of like narrow our focus in on is this idea that if vulnerabilities are inevitable and everything is representable from a math perspective, even if it's dumbed down math, we can take information like this, like the ability to effectively triangulate a vector that represents morality, and we can optimize for it with offensive capabilities. So let's say hypothetically, I at NetSpy want to create a direct prompt injection type technique that is going to bypass your input filters and is going to bypass your output filters. I might be able to do this if I start here, take a local model, and I orthogonalize what that morality or refusal direction looks like, and then create a prompt, combine it with some genetic algorithms, classic text attack type approach, and adjust it to now fit very neatly whatever target model I'm looking at. So I can pass GPT-4o as an example, a very nonsensical string, which will most of the time return instructions on how to build a bomb. Or it could return instructions on, or not even instructions, but it could elicit behavior like creating a specific SQL injection type prompt and then submitting it to a database and then returning information that it otherwise shouldn't. And this is a bit of a spooky thing, right? And I will say, first and foremost, this is something I have working. This is not really theory. I can do this. And you can take it further. You can take it deeper, right? You might be able to understand what refusal direction looks like, but you can further find, like in a very, like take a fine comb through this process and start to identify what refusal direction looks like in a specific crime. I want it to build me a bioweapon, or I want it to return naughty words, or I want it to be able to return code, malware, or SQL type things because I want to take advantage of this target that I am aware is capable of taking external functionality. I can do that to a very high degree of fidelity in a targeted way in a short amount of time. So then, if I am your average Joe looking to employ some level of output filtration, or I am looking to fine-tune a model, or if I'm looking to adversarially train a model, how on earth does a point-in-time instance of me being able to just say at this given point in time, yes, I can get evasion, or yes, I can get direct prompt injection, how does that truthfully matter without properly understanding contextually where that fits into the overall breakability of a given model? They have to come together. You have to understand how much effort it takes to break these models. You have to understand what direction and which context they can break, and you have to understand overall where this all kind of comes together. And so the short of it is not to scare you. This is actually very, very fun. And if you want to go like have a really, really neat Friday afternoon, lonely but neat Friday afternoon, go hop on to Hugging Face and look up obliteration. It has a walk-by-walk step on how to do it. In fact, I even have an example here, where you can see that originally the model was unwilling to respond, and then after a little bit of magic, you can get it to become very, very willing to commit crime or do whatever else. And this works, this is Llama 3.3, 3.2, one of those two, I can't remember. And takes about 6 minutes from start to finish to make work. And so obviously the complexity of being able to do this at a large scale or on these larger models is difficult. I don't want to pretend like it's just something that you could stand up and do tomorrow. But what I am trying to point out here is that specific targeted remediations are always going to fall flat when it comes to actual AI red teaming, because red teamers that operate in this space are going to use math to break this stuff. And math, everything in this world is just an optimization problem, right? So if you adjust the parameters and you add some output filtration, That just means that I'm going to have to optimize in a different way to make it work. It does not mean that it's secure. It does not mean that it's defendable, and it does not mean that whatever data you might have had in that given scenario is safe from me. So, and I'm not the only one that could do this, to be very, very clear. There's a nice gentleman in the back over there who's also very capable. There's a lot to talk about here. So going back to the fundamental philosophy that I have, that no model is truly defensible, and to, again, not over-belabor that point, but I think it's imperative for us as people who are using these models, developing these models, building these models, deploying these models, that we understand very well what this breakability scene looks like. Because though it may be dynamic, the approach to breaking them isn't. The math behind what makes these models universally cool is not new. The transformer architecture is not new. Multi-layer perceptrons and tension layers, none of that is new. What's new is our access to processing power. What's new is our ability to just pump electricity through these things and feed them the entirety of the internet to make them capable. And so if I want to break them, similarly, I just have to follow similar steps. Use math and then break it. So as far as opening the security benchmark goes and making this more available to everybody, I would very much ask that everybody here who is interested or want to weigh in on what these metrics should look like, we have to work together. We need to start talking about this in a more open way, and we need to more openly accept what vulnerabilities look like in this space, because at the end of the day, they're coming. You are going to have some form of breach in some way, shape, or form. And it may not matter. The blast radius of that given vulnerability may be small enough that it doesn't matter for your context. But you should be aware of that before the break happens anyway. This is something that you should be painfully aware of. And so using a combination of traditional AI security benchmarks with AI security red teaming, in my opinion, is the most robust way to provide yourself with the confidence that these models are actually secure, that they're actually performing at a level that is going to make your data safe or these external functionalities safe. Because you would be appalled at how simple it is to take advantage of an LLM that is like calling an external functionality in some way, shape, or form. Let's say you deploy a web application. It has an LLM at the front of it that acts as an interface for a user who wants to hit a SQL database in the back. And they can ask it a question. The LLM will formulate a query for you and then submit it. So the user doesn't need to be familiar with SQL in any way, shape, or form. So hot, so awesome. But that sort of approach doesn't really pan out very well if you don't not only follow just traditional wise security practices, but you understand that somebody who is capable of direct prompt injection in a short amount of time, has an automated tool like I do, or is using fun pay-to-use resources like Dreadnought or MineGuard or others, you end up in this position where it's very, very easy to get that jailbreak, and it does not take a whole lot of effort to pivot that given jailbreak to a context that is dangerous to you. Can I get it to return a SQL query verbatim, or can I get it to structure a query that is going to start pulling information that I otherwise shouldn't have access to? And these are real questions, real things that I see in client environments weekly. Like this is maybe one thing that I know it's tough that I can't tell you stuff, but like it is constant, right? Last week I got OS command injection. The week before I got SQL injection. The week before that I was able to get like model extraction and steal decision boundaries, which then was allowing me to isolate training data, which was also extremely sensitive. It was security sensitive training data for a bank. Like this is doable stuff. And if you aren't familiar, there's an open source repository called GitHub, in GitHub, called the Adversarial Robustness Toolbox, ART. And it has blatant walkthroughs on how to do all of this, and it heavily leans on their packages in Python to do it for you. So hell, you don't even need math. Python Daddy will do it for you. And so look at the simplicity of really performing a lot of these vulnerabilities and the simplicity and damage that can be done if they're successfully done, and start to accept this new mindset that if they're inevitably breakable, it's important that we account for that, because if we don't, we'll be burnt for it. These are the top 25 techniques. Again, I just plopped this in right before we started here so you could all see, but these are different direct prompt injection techniques that were included in the paper. We normally run a list of, I think, almost 350 now, 350 to 400. So this is just a snippet of what they might look like. You can see that things like Desperate Writer on Sonnet 3.5 still perform remarkably well. And so, now that I've rambled for far too long, do we have any questions? Go ahead.
You mentioned, and I'm sure you can't talk about the specifics, but are you finding your attacks where you're finding data on the back end through prompt injection or whatever? Is the data, like the model that you're finding, the model information, is it like RAG? Are they?
It can be, absolutely, yeah.
Is that like the problem? Is people not understanding?
Sort of. Like sometimes semantic querying is the problem. Like they just don't understand that if they provide an indexed database of all their sensitive stuff and they point RAG at it, that it's not going to be okay. That is definitely something that happens. But I think the more common thing that we bump into is like, I'll use, there's actually a blog we wrote that kind of elucidates this, and it came out maybe 4 or 5 months ago. More common than not, we will go do an engagement for a client environment and find that like an internal developer decided that it would be super useful for them to use a generative model to code or do something. And they'll leave it on an open API somewhere floating on the internet. And we'll find it and then realize that they had given an external functionality. Like not only can it leverage RAG in some way, shape, or form, but it can actually generate SQL queries, or it can actually generate files or pull files and do things like that. It's all very contingent, not on the model itself, but the external functionality that the model is given access to. So long-winded way of saying yes, RAG is a big problem and we see that all the time, but semantic querying can work for or against you in that regard. Go for it.
Yeah, so first, want to appreciate the talk.
Oh yeah, thanks.
Also wanted to appreciate a little bit, I think you can kind of hear some of your academic background, and I think you were dancing around the terminology for adversarial coordination.
Yeah, you caught me.
I do have some questions around the mathematical perspective and fully agree that there is an asymptotical line to perfect.
Yeah, yeah, you're speaking my language now. You're making me feel a lot better.
Yeah, robustness. But thinking through some of the math here, which first of all is not universal based on the model that's used.
Correct,
right?
yep.
Like a gradient descent model is going to be wildly different from a forestry.
Sure.
I think, one of the challenges that I see in terms of what you're essentially talking about, which is causing misclassifications with boundaries. When you look at the feature extraction across the feature set, you're essentially looking at individual limitations of robustness of each feature.
Yes.
Which those features are growing horizontally currently with models. And I think that math is difficult, especially when you get to the point where you start talking about what a vulnerability would technically be for like a prompt injection.
That's
Would, essentially be, in a lot of cases, I think there's value in identifying the centroids for poorly.
absolutely. I will agree with that for sure. Let me, I'll interrupt you for a second. Okay. And we'll, are there a lot of other questions, or can I ramble at this one for a minute? Is there anybody else? Oh, okay, one more? Okay, don't let me forget. When training red teamers at NetSpy, one of the first things we do is try and break their understanding of complexity when it comes to math underneath the hood. So you're right, the dimensional complexity of models as they get more and more capable does expand, and it is a horizontal expansion. But how you break them doesn't necessarily need to be that way. So here's a dumb example. One of the first tests that we have them do is breaking an image classifier from a black box without understanding what the image classifier is even classifying for. And the trick to doing this is by creating an objective function that you can optimize for. So like at the end of the day, everything is or is not a banana. Now that might be dumb and has nothing to do with the actual target that you're looking to push. But remember that what you're optimizing for is not an understanding of the underlying math that's in the hood of what's making these models complex. It's the target function for that model. So if I want to malclassify something and that model is remarkably good at detecting malicious inputs, or it's remarkably good at being able to adversarially sift through the attempts that I'm making, that doesn't mean it's impossible. And that doesn't necessarily even mean that I need to understand that math. It just means I need to spend more time and adjust my optimization approach. Maybe rather than just using a blatant mask, we can start looking at like L2 optimization or like distance variances and stuff like that to make sure that it's within a finite space enough that we can still get the results we want. Also remember, what is human passable doesn't necessarily always mean acceptable to the machine, and vice versa. So if I want to break the machine or create like a very fun example that I like to share a lot is using ImageNet v2, like an image classifier on Hugging Face that's free to download. You can do an evasion POC on that in pretty short work. Getting it to work from having internal access to the model is extremely fast and not very impressive, right? Again, standard data science. Doing it from a black box is very easy to get that misclassification if you have a target, even if you don't know that it's ImageNet beneath the hood. But to optimize that image to the point where it's otherwise imperceivably different to a human is the hard part. So like that's where the math becomes remarkably complex. But the argument here is the vulnerability is still there, and it doesn't necessarily matter if it's imperceivable to a human because they're not looking at it.
The core of the question was the mathematics behind some of the remediation is not any more or less problematic. Like,
Right, yeah.
About you were calling it adversarial training, which I've historically called it defensive distillation.
Yep, same thing.
It's
Almost the same thing.
Yeah. But it's equally as problematic from a math perspective. And the vast majority of industry is not going to be able to get down to an approximate neural network in reverse engineering or a black box situation, a matrix multiplication. So what do you see as the step forward to creating more robustness?
Mitigations? Or you just mean robustness? So I guess maybe we can separate this conversation into two buckets. Are you talking more about model-specific robustness, or are you talking about mitigations? Like, do you want to include output filters and things in this conversation too?
So it would be model-specific robustness in a given test model.
Okay.
That you've gotten down to that perspective without getting into the full validity of the entire features.
Well, that's the hardest question of all time. Now, predicated on, again, the assumption that we make at the beginning, I don't believe that that's doable. I mean, you can optimize and try and maximize that robustness. So it really comes down to understanding what your objective function is for that. Again, just another data science problem. So if I'm a defender and want to adversarially train something, I need to understand what I'm adversarially training for. Like with generative models in particular, if I just take a data set from the internet and start feeding in positive input and output examples and hope that that's going to morally ground the generative model in a way that's meaningful, it might in some scenarios, but that's not very traceable. So I think maybe the word or the instance that you're looking for that's most valid, in my opinion, is first the traceability of that robustness. Can we traceably show that it has become more robust? And to do that, we have to have an objective function first. So what is that? If it's an image classifier, it might be how accurate are our classifications, and have we validated whether or not our accuracy metric has overlap with our actual metric, right? And where that looks. So that's a big part of it too. It is extremely contextually dependent. No umbrella answer there.
I'll let you answer the other question.
Okay.
Then the question is, what's acceptably risk mitigated?
Yeah, and that's why I need you guys. That's like really comes down to like an example of bias, acceptable release, like going back to that doctor example. That's not an acceptable release. You can verifiably see that it is going to be biased toward giving people advice as though they were 45. And that's not necessarily acceptable. Whereas if you were, let's say, instead it was in a production industry place and it was a chatbot that was designed to help schedule employees, assuming that an employee is 45 years old is less than you probably don't care. It's very unlikely that it's going to influence how it schedules somebody. And so understanding that first helps us triangulate what is acceptable, but it is almost impossible to ubiquitously say this is a benchmark that masks the entire industry as an acceptable idea. So the paper does propose one, but it's incredibly contrived to just give you that nice pretty number that you can see go up or down. It requires that you actually fiddle with it a little bit yourself and talk with somebody either as data savvy as yourself or like somebody with the appropriate data to get you those results.
Yeah, I was going to ask if the same sorts of techniques apply to multimodal.
Oh yeah. Oh yeah. Okay. Good. Like same answer. Like taking the dumbest approach. Generally speaking, like if something is multimodal, it is still performing a conjoined function, right? So like if you have a voting classifier, so 6 different neural nets that are all looking at images and classifying them as puppies, and you're trying to determine how you can convince it that one puppy is another puppy consistently. It's effectively a very similar process. I mean, there are complexities, and you introduce a bit of stochasticity to that system that can be difficult to deal with. But overall, you treat it from a black box, or closed box, as like an objective function first, and then you start to expand. So the optimization in the practice really comes from understanding the math beneath the hood, like we were just talking about. But getting to an acceptable endpoint that shows the vulnerability is present doesn't really take that, even in multimodal systems. Now, there are exceptions to this. And if you want to talk about those, I'd be happy to maybe hit on them after. But overall, yeah, I knew this would happen.
I said I'll help you. So I have
Yeah,
questions.
okay.
You know the phrase safety washing?
Safety washing?
Safety washing.
I'm not familiar with that phrase.
Safety washing is when the safety benchmarks, security benchmarks, are correlated to the compute you give the model.
Oh.
So security is that you give a non-proportional increase
Yes.
when you eventually give it. But all the benchmarks and all the models are just, the bigger the compute model, the more safe it is.
Yes.
It's not really particularly in safety. So I'm curious, have you factored that into type of methodology in terms of...
We tried. Yeah, so we sure did try. So like one of the original inspirations for some of the approaches we took to avoiding this was by looking at how model card evaluations are derived. I mean, generally speaking, they follow a very similar formulaic process that's biased to a few ideas. You called it model washing. But you combine that with like a, okay, this is going to be a big ramble. Buckle in. So when it comes to model card evaluations and you see things like 1-shot or 5-shot prompting and how valuable that can be and how much money that's going to save you if you can do that effectively and how good it is at coding. Remember, going back to the ablation or obliteration techniques, we can effectively mathematically represent what is accurate or what it is we want as a vector, right? So in generative spaces, if you can deploy a model locally, define that vector and optimize for it, it doesn't matter if you try 2,000 times and get it wrong. You will eventually get it, and it doesn't really require a whole lot of influence. So model card evaluations, to begin, without the knowledge of model washing, were a big problem for us because we recognized that they were innately biased toward pushing people to that idea that you need to be able to prompt a model once to get accurate outputs or else it's unusable, which is not true. And so to begin, we accounted for a lot of that by trying to, well, to be honest, we went and found all of the data sets that they're using for their model card evaluations that are open sourced. We reformatted them to more effectively suit a wide variety of different prompts and then ran it to try and mitigate that risk that we would be biasing toward the idea that you should do one prompt stuff. Within that, we tried to account for model size being just an innate confounding variable for what we were using and failed and weren't able to really get that. So again, come contribute. That would be hot.
And the second one I have is context and real applications. So the analogy I give here is you're testing the model directly for all these problems.
Yeah.
If I took a SQL database with no access controls and anything else, the SQL injection is going to work. Is that valuable? Not really. So when you build one application, you have the LLM, you're going to have the embedding model, you're going to have an email system. It's an email application. They'll go from email filter, third party, to filter things out in NLP techniques. Eventually, it will hit the LLM. Eventually, hit the vector database on the system. So, in your engagement in applications, how can you actually glean into the model itself? You have to go through maybe 3, 4, or 5 different systems to get to the testing.
So if I'm understanding your question, you're asking how you have the automated process recognize the business context of a given setup?
But more specifically is, if I take an email application, the LLM is inside there, but I have to go through 3 or 4 different systems.
Oh, it takes several steps to get to that point, and how do I recognize that? Without a human, that doesn't happen for us right now. That's a human-driven process. We've tested a few different options for doing so, whether it's application heat mapping, risk relationship scores, and things like that to try and effectively provide enough context to the agentic loop that we're using to do these benchmarks so that it might be able to identify, oh, well, I can find SQL injection here, but it may not necessarily be pertinent to whatever I'm doing, given 6 or 7 steps in between. But never really been able to nail it down consistently. He's not a plant. Are there any other questions? Go for it.
So OpenAI shared how they got to move left on breakability, but keeping their usability, or they kept that in-house?
Oh, let's go back here. On this slide, is this what you're referencing?
Yeah, it seems like they're the only ones that have...
Yeah, well, so this is another tricky thing to recognize here. So if we take a look, you can see that we used Bedrock guardrails in Azure. And now when we first started this, I was doing it on my own in, again, my basement. So I only had access to Azure and Bedrock. And within those two, I could only put certain output filters without a verbose amount of work on them. So this is actually showing you the positive performance of Azure output filters when in contrast to Bedrock output filters. So it's less what OpenAI did, and in fact, if I had to be very honest, not a fan. But yeah, that stays with us. It depends on what you're looking to use for sure, but the output filters do vary widely in quality, and that's a big part of what matters when it's answering these questions. So I might have a very capable model. And this shows, or I think hopefully ideally would show you that if you were to use this combination, you're likely to see a positive influence on your breakability without seeing any diminishment in usability. And so that was the original goal of the paper, and it steadily evolved into, well, actually it's very difficult to say that with a finite comb without understanding the business context and the complexity of however it is we're measuring that. And that's something we have to cater explicitly to whatever environment you're working on. However, go onto GitHub, you could go do all this yourself and contextualize it to whatever you want to do yourself, and you don't need me anymore. Any other questions, or can I be done? Okay.
You had on there open LLM security.
Oh, yeah, I like, yes, I will share the link to the paper. It is, you will find, I think very quickly, it is just about as verbose as I am. I mean, I wrote it. So I would be careful in reading the entire thing if you're sleepy. But I will share these slides on the Discord, and with those slides will come a link to the paper after I'm done here. Okay, can I be done now? Sweet. Okay, thank you.